Good afternoon, everyone. Today I will explain to you implementation feedback circuit on a flash-gate sensors. Magnetic sensor is a device that can measure the magnitude of a magnetic field and or its vector components. The list of most commonly used the sensor is given in the left side figure. There are three main types of the sensors in the sensor industry. These are acute sensors for using detecting very small magnetic fields, flash gate sensors for detecting small magnetic fields, and Hall sensors for detecting larger magnetic fields. Flash gate sensors are among the most preferred sensors that measure low magnetic fields because speed sensors are expensive and impractical due to the need for quick charging. As can be seen, magnetic sensors have wide application areas such as determining orientation, satellites, and control systems, high reliability, non-contact switching in aircraft, non-destructive testing of metals, detecting tiny magnetic fields produced outside the brain by the neuronal current, etc. Fundamentally, a fluxgate magnetometer consists of two parts, an electronic structure and fluxgate sensors. Electronic structure is composed of drive electronics, which is used to drive the sensor, and sense electronics, which is used for extracting magnetic field information from the sensor output. The typical fluxgate sensors consist of a sense, or the other name is pickup coil, surrounding an inner drive or excitation coil that's wound around the permeable core material. Fluxgate sensors divide into three categories: those employing rod course geometry, ring course geometry, and the racetrack geometry. The most common type of sensor used in magnetometer application is ring course sensors because of the having a lot of advantages on the other configuration. It has a balance of the ring course symmetry and the pickup coil, a uniform distribution of possible mechanical stress in the core, and the magnetically closed path, which provides lowest noise sensors. The working principle of the fluxgate, which is based on the Faraday induction law. As I mentioned before, sensor consists of core having hysteresis curve slope of high gradient, a primary coil, and a secondary coil. In figure A, the primary coil of the sensor is excited using AC square wave signal, having an amplitude large enough to saturate the core. The core saturates evenly in negative and positive cycles. In absence of external magnetic field, the flux generates in two halves of the core cancels each other, and the total flux is zero. In B, in presence of ambient magnetic field, the core saturates unevenly in two halves of the core. And the secondary coil picks up this imbalance in the magnetic flux due to the ambient field twice per drive cycle. This generates the second harmonic in the pickup coil, having frequency minimum twice the drive frequency. Therefore, the information about the field can be derived from the even harmonics using the second harmonic electronic circuit. The preparation steps of the sensors are summarized in that figure. The most critical element for the sensors to work properly is the soft magnetic material. In this work, cobalt-based alloy material was used in the design of the sensor. This material is wrapped 6 times around the hoop made of thick material, and ring core is designed. The thickness of this magnetic ribbon has been chosen to be at least 55 millimeter in order to contribute to low noise performance by reducing eddy currents to low power consumption. The dry toric coil was obtained by wrapping 130 turns around the core with 300 micrometer copper wire. The completed rings with excitation coils were put into a pickup coil housing, which was constructed to hold the sense coil, shown here. Finally, the sense coil with 500 turns of copper wire having a 200 micrometer diameter wraps around pickup coil housing. The pickup coil was wound diametrically on the bobbin and is used to detect the magnetic field parallel to its plane. The flatgate sensor is based on two custom ferromagnetic ring cores, which are periodically driving into magnetic saturation by using toroidal drive windings connected in series. Connection of two toroidal drive windings in series reduces power, volume, and mass by removing the need for third ferromagnetic core. We use method the second harmonic detection for field extraction from the induced voltage waveform on pickup coil, because the second is usually highest even harmonics. The block diagram of a magnetometer electronics based on the second harmonic detection in shown figure. The excitation coil current which saturates the flatgate is produced by power amplifier block. A frequency of the excitation current is determined by the signal coming from the generator block, which also produces a signal whose frequency is twice for a phase-sensitive detector. An electromotive force proportional to the amplitude of the magnetic field along the sense axis will be developed in the sensor secondary. The voltage induced in the pickup coil is then amplified, and a bandpass filter usually delays the first and other series harmonic. Then the phase-sensitive detector selects the second harmonic, which is filtered by a low-pass filter and integrated by an integrated block to get a sufficient gain. The signal so obtained is then used to feed the compensation coil, which produces a field whose direction is opposite of the measured fields. Therefore, this magnetometer is a closed-loop system, work as zero indicator. In drive electronics, square wave excitation is most suited for the sensors due to its lower power consumption and simplicity in implementation. Here, we used 4 MHz crystal oscillator to design a square wave oscillator generator. Then, for a frequency divider that's capable of dividing input clock frequency by means of a certain factor, we use the dual D-type flip-flop that divides the incoming pulse frequency from the incoming square wave. The oscillator and divider can only produce a few tens of milliampere at most. So these outputs cannot be directly used to drive the core saturation because sensors requires many amperes. Therefore, in the excitation generator block, we use the Class B push-pull power amplifier for efficient bipolar current amplification. Fast-speed sensors was excited with about 80 milliampere, although power amplifier produced about 33 milliampere because we use tuning capacitor parallel to drive winding. And here you can see the excitation waveform. In sense electronics, the output of the sensor should be resonated at the second harmonic frequency with an appropriate capacitor. Due to, as mentioned before, the second harmonic produces the highest sensitivity and the lowest noise. If the secondary is resonated at the second harmonic frequency, the EMF will approximate a sine wave, which is named modulation signal, and will have a much greater amplitude than that obtained without the capacitor. In this configuration, the pickup coil works in a dual capacity simultaneously as a sense winding and as a feedback winding. After this resonated stage, it becomes possible to extract information on the external magnetic field by synchronous demodulations. After here, demodulation was accomplished with a phase-sensitive detector, a CMOS analog switch following the preamplifier. The sensed magnetic signal fed into the synchronous detector and exits as a DC signal, which is amplified by DC amplifier. This DC value feedback into the sense winding, which also as a magnetic field generating solenoid. In this manner, the integrator feeds sufficient current into the winding to bring signal output to zero. Under this condition, the core always sees zero field when balance is reached. Since it always works under zero field conditions, its normal linearity caused by variation in the magnetic induction versus applied field non-existence. The wide dynamic range of the magnetometer results from the use of switching multiplier as a synchronous detector or demodulators. Demodulators for signal recovery are supplied with a reference signal which is precisely synchronized with the modulation signal. In general terms, operations depends on the high degree of correlation, which is known to exist between the periodic demodulation signal and the reference signal. Phase-sensitive detectors performs this AC modulation signal to DC conversion forms the heart of the instrument. Then PCB consists of a mixer and a low-pass filter block. The modulation signal is mixed with reference signal in the mixer stage and then applies to an adjustable low-pass filter block. This method is also termed demodulation and isolates the signal at the frequency of interest from all other frequency components. The switch gain amplifier is most important block of this demodulator. The key to operation of the PCB is the two-stage switch, which is controlled electronically from reference voltage. The switch change position between points A and B as the reference change polarity. This action gives a systematic change of gain between +1 and -1 in the signal path. In the below left side figure, the sine wave signal and applied reference are precisely in phase. The reference changed polarity in a symmetrical fashion in step with the signal, and so causes full wave rectification of the signal at the switch output. The output of the switch is then applied to a low-pass filter, which smooths out the ripple component and delivers a DC voltage, which is proportional to the amplitude of the signal. However, in most applications, the signal and reference will not arrive at the phase-sensitive detector exactly in phase. Hence, on the right side, figure A shows the effect of phase reversal, giving a negative DC level. Figure B shows the output when the phase displacement is 90 degrees. In this case, the output from the switching stage is a bipolar waveform that averages to zero and gives no net response from the low-pass filter. Finally, in figure C, output at some intermediate value of phase shift, giving a DC level somewhere between positive and negative maxima obtained by 0 degree and 180 degree phase shift. To determine exact relationship between signal and reference, we recognize that the switching operation is equivalent to multiplication of the signal by a square wave, taking values +1 and -1. Here you can see the flux gate magnetometer, which I explained working principle and signal processing electronics. I'd like to state that the ferromagnetic part of the sensor has the main role on the performance of the magnetometer. The selection criteria of the ferromagnetic part are determined by the type, geometry, and the operation aim of the sensor. So it's difficult to give a list of either properties. However, some general requirements may still be useful. These requirements are high sensitivity, good resolution, wide measurement range, low noise and lower consumption, etc. DC function parameters of the sensors, such as sensitivity, linearity, accuracy, and non-orthogonality, are determined using these DC test setups. First of all, the magnetometer was placed in a central position in the Harmonic coil or solenoid. These different DC current values were applied to coil, and the magnetometer output was recorded using a LabVIEW software web program. The bottom right side graph shows the variation of the second harmonic signal intensity depending on the applied DC magnetic field. The scale factor of the sensor was determined from the slope of the regions where the obtained data showed linear behavior, and the points where the deviation from linearity began were indicated the measurement range of the sensor. According to this graph, the scale factor of the sensor was determined as about 30 kilowatt per Tesla, and the measurement range was about 80 microtesla. For the noise measurement, dynamic signal analyzer and mu metal chamber was used. Firstly, magnetometer were placed in a multi-layer mu metal chamber insulated from the external magnetic field. The graph at the bottom right shows the frequency-dependent noise level of the device. According to the noise level of the magnetometer at 1 Hz was determined as about 1.1 nanotesla over square root of Hz. To obtain the bandwidth of the device, the AC test setup is shown in the figure is used. In this test setup, solenoid is fed with an AC current, and the sinusoidal output voltage of the device is monitored simultaneously in oscilloscope. The frequency of the solenoid current is incremented with steps 5 Hz from DC until the magnetometer cannot catch that AC magnetic field created by the solenoid. The frequency at which the magnetometer is unable to follow the AC signal indicates its bandwidth limit. Based on the test results, the bandwidth of the device is determined as about 100 Hz. In addition to the measurement I mentioned, tests such as EMC, EMI, thermal vacuum, vibration and shock, and radiation were also applied on the flux gate magnetometer and resulted in a success. As a result, the key experimental results of the magnetometer, which we have produced especially for using satellites, are summarized in the table. To determine performance parameters, all the measurements and characterization tests have been performed in the magnetism laboratory of Scientific and Technology Council of Turkey. The significant experiment result of this magnetometer power consumption and wider operating temperature. Thank you for listening.
Maybe I have a question.
Yes, Ivan.
For testing, because you show that you have some kind of mu-metal chamber. This mu-metal chamber is used for somehow diminishing the effects of Earth field or some parasitic fields, but it is passive kind of shielding, yes, and you use also some kind of active shielding that somehow to compensate the Earth field or some by some kind of magnetic coils or
Yeah.
during the testing.
Yeah, actually, you are right. Inside, now we are working over inside the mu-metal chamber. We are inputting an three-axis Helmholtz coil. Even if due to some temperature changes or other external effects, to avoid such effects, an active Helmholtz coil system is considered in the laboratory. For the remnant field, even if the Earth field was compensated with the mu-metal, for example, if the external temperature changes, the residual magnetization of the mu-metal also changes. To avoid such effects, we think an active Helmholtz coil inside the mu-metal.
Okay, thank you.